Yes, James-Stein estimator.
Yes. So this guy came up with a very weird kind of estimator, which is this. So Y is your data, and sigma is the usual standard variance term, and then theta ls is my least square. So he said instead of using theta ls, use something like this.
M. What is M?
M is your number of regressors.
Oh, okay. So then,
Right? So he's saying
why is this better? Or is this
he's saying this is always better than least square in terms of MSE.
sometimes these numbers just seem so random. So Jay, like M minus two. Like why
Yes.
is the minus two just seems so random?
In this case, I don't have a good explanation. Uh, I don't have any. I mean,
No, no,
maybe
no,
he
no
did the
worries.
algebra and got that.
Yeah, exactly. Exactly.
He did some algebra and got that. So this is like was supposed to be like a very very shocking fact at that point because people used to think that least squares is best you can do in terms of linear at least when like there is no stability problem and all those things.
Hmm.
Least square is best you can do. So there is a result called Gauss-Markov theorem, which
Okay.
says that among linear estimators, least square is best.
Okay. Right.
Okay. That way this the loophole here is that he has this absolute value of y square in the denominator, which depends on the y. And because of that, this is not really linear, but in practice, it behaves very close to linear. And then he's saying it is better than linear.
Got it.
And this also has some like other interpretations of nonlinearity. And okay, so there is this area of statistics called decision theory. Have you heard of it?
Yes, I've heard of it.
Yeah, yeah. So this is about like a formal setup of like solving statistical problems by casting them in terms of game theoretic notation and everything.
Okay.
Okay, so they try to borrow the game theory from economics and apply it to statistical problems, and what you get is decision theory. This is Second World War time people discovered that you can do such things, like very interesting stories and all. I won't go into that, but so in decision theory, there is a concept of dominating or dominated estimator or dominated decisions. So if one decision is always better than a second decision, then you never do the second one, right?
Right.
Like no matter what scenario, my first choice is always better than second.
Right.
So this was the first time people showed that the least square is dominated by something else, which is the James-Stein. And then does that mean the least square is always bad? Not necessarily, because under scenarios where it works well, least square is still good. But there are some non-intuitive ways of improving things. And the reason this really works is when you do this mean square error kind of thing, whenever you are squaring the error, that means the large errors are getting much more weightage than compared to small errors. That makes sense.
Yes. The large
So
errors
if
are
your error
taking over
gets
for.
getting because it gets squared, so error of 100 becomes 10,000 when you
Yep.
square it.
Yep.
Error of 5 becomes only 25. So large errors gives kind of undue high weightage for that. So as a response to that, people look into something called more robust estimation of methods and all. So that's another area of statistics where you do robust estimation. And the idea behind that is you don't give as much weightage to outliers and all. So how do you take control of things where the one or two outlier points won't have too much weightage? So you try to detect the outliers or try to get the influence function that we discussed last time. One
Right.
single point have a lot more influence, so try to get the influences down. So there is some like a lot of study around those areas.
Wow.
Okay,
Okay.
so that's all I wanted to add on that. And then there is a more general setup with Bayesian regression.
Bayesian
So
regression. I didn't know that was that's another type of regression.
Yeah, that's another type of regression. That's rather
I was,
instead of
wait,
type
can
of
I
regression.
guess? Can I guess? Maybe
Yes.
this is a dumb guess.
Yeah.
Because I was gonna ask, we really
Hmm.
haven't talked about the distribution of this data given everything too. Does it involve some sort of
Uh, we discussed a little bit. Let me go back to the first of. We discussed least squares and then we discussed Emily. And doing Emily, we assume that the errors are normally
normally
distributed.
distributed? Okay. Yeah.
And then that gives basically distribution of everything. You get distribution of y, and then you get distribution of beta hat. So you could calculate the expectation of beta hat, variance of beta hat, and all those things.
Okay.
Okay.
Bayesian
So the
regression is a whole
Bayesian, what this does is it says that the beta will have a prior distribution.
makes sense. There's a prior. Okay.
Okay. And then you can calculate the posterior and then get the posterior mean and all those things.
Gotcha.
Okay.
That so
Now
that
it
builds on, but that's aside from, so I guess like linear ridge and lasso, but then Bayesian is kind of building again back on the, I mean,
yes, on
building
the linear, yes,
on your
on
side.
the Emily and all that.
Yeah. Okay.
Okay. Now it turns out that in the Bayesian framework, if you choose the prior to be normal, then you get ridge regression.
Yeah. Yep. That makes sense.
That makes sense. And then you choose the prior to be something like a double exponential, then you get lasso regression.
What is double exponential? Sorry.
It's another kind of distribution. It's like exponential, but it takes positive and negative values.
Oh, okay. Gotcha. Okay.
Normal exponential takes only positive values, so you want to basically do symmetrify this,
Okay. On the other.
then you get double exponential.
And
So in that sense, the people who follow Bayesian theory will say that ridge, lasso, linear, all these are subspecial cases of Bayesian.
that makes sense. Okay. Okay.
So they put all of these under a single framework umbrella.
Okay. Got it.
So that's what is happening.
Got it.
Okay. So that's mostly about it. That's mostly like all the things you can do with linear regression kind of setup. And then of course you can like as we discussed, we can add more and more regressors and add more higher powers. Like if you have one regressor x1 and x2, you can add x1 squared, x2 squared, x1 times x2, and then maybe cubes and fourth powers and so on, and keep adding regressors. And eventually this becomes bad. So you do variable selection. So that's how practically it works.
That
You keep
makes
adding regressors, but you also try to keep it like under some control. So you try to do some variable selection, and that's it.
wow. That makes sense. Okay, so Jay, I'm looking at the schedule that we have coming up here.
Okay.
The next
Let me stop
class.
sharing.
Oh yeah, I'll stop recording here too.